All right. So like I mentioned, we're going to go over section 27, right? So this is going to be, hopefully I have that right, calculus, gradient descent, basically your introduction to saying, okay, like, well, it's kind of motivating from our linear algebra aspects. Like, oh, we can use linear algebra to actually perfectly find like linear regression, right? We can actually figure out what perfect line of best fit. But I kind of mentioned last time is that what was one of the issues with trying to find it through a system of equations for this line of best fit for at least linear regression?
The more features there are, the more complicated the math gets, and the heavier it gets computationally.
Exactly. It's good. As basically you get a more and more complex model, basically more data points, more, what's it called? Features. Basically it goes up with, I think with number of features, it's like n cubed. So big O notation. So to kind of put in perspective to order a list, usually we can do that within like n log n time. Which is like a little less than n squared, but n cubed basically is just like exponential. So it basically becomes really difficult as the model gets bigger and more complicated. So it's not necessarily the best example or best solution. It technically will give you the perfect solution. It will tell you this is the best, like the line of best fit. This is the best one you can get, but in order to get to that point, it might be really hard. So we're gonna basically kind of cheat the system a little bit by essentially basically making a lot of guesses and get a better and better answer. It won't necessarily give us to the best answer, but it'll probably get us close enough. And also note that we'll talk about being like, it's not necessarily just guessing out of thin air. We'll actually kind of do some educated guesses to basically make it better and better. And that's going to involve using calculus. Okay. So, so today's stuff will be mathematics in that repo. So we're going to start off with derivatives. So I'm going to ask you guys first is, I've done this in the past where I've talked about derivatives. Just a kind of thumbs up, how do you guys feel with calculus, like just at least the derivative aspect of it? Okay, I see most people thumbs up, Jane, a little, maybe not, right? So I'm gonna just kind of quickly just talk about this. And I'm not gonna harp too much on like what calculus is, but there's some aspects of like derivatives, I think, that are kind of important to understand. So one thing, you always hear probably derivatives as a rate of change, right? And so just kind of like, it's kind of one of those things like no one talks like that. Like no one says rate of change or changing rate, at least not anyone I really know. So one way I kind of think about it is slope. Basically, a derivative, all it's saying is saying how steep is it at a certain point. So if you imagine like a graph that's a funky little function, like this guy right here, what our derivative tells us is saying how steep is it like at this point, right? And then say, okay, well, how steep it is, well, that we can draw like a tangent line. If you remember back in calculus class, right? We can draw a tangent line, and then eventually we can approach that into essentially our derivative. This is kind of like how back in like probably when you're first introduced to like what a derivative is, you can say, well, I want to know what the derivative is or the slope at this point right here. Well, we can estimate that by drawing it from here to here, right? And you say, okay, well, that gets us a line, right? So that's like a secant line, if you guys remember the terminology. Not really super important, but just know that's what it's called. And you'd have this line here. It's like, okay, well, this line, going through, let's say from here to here, gives us a slope here. It's like, well, that's not quite right. So we make it smaller and smaller. So basically, instead of considering this point and this point, we kind of consider these 2 points closer, and we get it closer and closer and closer and closer. So our tangent line or our secant line gets smaller and smaller and smaller and smaller until basically we go infinitely small in mathematics, taking the limit, right? And with that limit, essentially, we say, oh, that becomes the tangent line, or what we just call the derivative. So the tangent line is the derivative, and essentially that point at that the slope at that instantaneous, or the instantaneous slope at that point. Instantaneous meaning just like at that very central point. In mathematics, we can define things as exact. In reality, we really can't, but that's close enough. And really what this is right here and this thing, these are really the same things. So you might have seen like kind of a quick show of hands, like who's, like I think you guys might have even seen this like probably when you guys were interviewed for the coming into the course, right, is this kind of function. And all this is really representing is like, hey, take the point, if you had a point here, x, and you move a distance delta x. So this is like delta x, like at this point. It's like, okay, the derivative, and this really should have a limit, but basically it's like, okay, take from this point to this point and say, okay, this function is saying, okay, this is the y value, this is the y value for x plus delta x. This is the y value for just x. And then we just have the change in x direction, and that gives you your rise over run, so your slope. And then we just make this as small as possible with the limit, and then boom, you got the derivative. Okay, so makes sense, hopefully. Like, all right, cool. Yeah. So if anyone ever like asks me, it's like, like, what's the derivative? I'll just say it's the slope. Like, that's pretty much all it really matters. Okay, cool. Simple enough. And then we get into the different parts. So note that basically the rate of change for nonlinear functions, we can still make a derivative itself. Like I said, you have a line, basically the line's derivative, the line's slope never changes. But if we have a nice curvy, funky function, the derivative will change. So kind of just moving on from there. I won't go over the basic rules for derivatives, but just know that the ones that you typically will really care about are the power rule, additional terms and coefficients, just knowing how to take a derivative essentially. One thing I'll kind of mention is like there's something called the quotient rule. Do you guys remember ever hearing about the quotient rule? Yeah, it's something because you don't really, I see a nod, I see a shake. Really, in reality, I always like to tell my math teacher this back in high school. It's like, I don't need to know the quotient rule, like, because it's the power rule with the chain rule. So basically, if you know the power rule and you know the chain rule, you can pretty much do like most derivatives that you'll find. Note that there's some other funky functions like, sine and like log and stuff like this, but technically they're all following from essentially the power rule and the chain rule. So just know the chain rule. Essentially, how do you guys feel about the chain rule? Like thumbs up if you're like, yeah, you do this. Cool. Just kind of remember is that basically if you can build a single function, some kind of like a function that you have, if you can say it's a function of a function, so that kind of like classic f composed of g. So basically what you can do there, essentially you just take the inner part, that inner function, take the derivative, and that's this part, and then take the whole derivative as if the inner function is like x, and there you go. So I won't go over that, but also you'll see it written like this too. So just know if you see this part, that is literally trying to say the chain rule. Just kind of showing you guys two different notations. Okay, and then last part, just derivatives. It's just basically is that we can use derivatives to find the minimum and maximums. So this is going to be really important because later on we're going to try to minimize how bad our guess is. So essentially we can use a function that describes how bad our guesses are and take that function and say, what's the minimum? What's kind of like the least bad we can do, right, compared for our data. And that will basically be using derivatives to basically find these, hills. And you can either think of it as like the bottom of the hill if you're thinking of something called the cost function. If you are thinking more in the sense of like something called a utility function, you can say how good can we do? You're going to maximize it. But either way, we can basically use calculus to kind of find what that direction is. Cool. Any questions on derivatives that you guys might have, or if that I kind of ran over real quick? All right, simple stuff. So we'll move on. Cool. So this leads us into gradient descent. So gradient descent here. Hope I have this all. Okay, good. I didn't run it yet. Okay, so I kind of already talked about this a little bit. Is the motivation of linear regression is that we can't really we could technically try to solve it directly with system of equations. It just turns out it's usually computationally expensive and take a lot of time for a computer, or we need a lot of resources. It's just not going to be a good like overall strategy. So one thing we can do is basically say, well, okay, what if we can like describe, like I said, how bad a line is. So like we have a bunch of data and we put in a line and we say, how bad is that line? That is something we call just the cost function. So for linear regression, that's essentially just the residuals or the error, so the RSS, right? So the residual sum of squares. But note that this cost function is very arbitrary, right? It's just saying, essentially when we say a cost function, sometimes we call it the loss function, right? Basically what we're saying is, this is some way we can measure how bad our prediction is, right, over the data. And so this will be really important because basically gradient descent was not just good enough for linear regression, but actually almost a lot of other machine learning algorithms, essentially trying to get a better and better prediction. Okay, so let's check out how we would write this, right? So I'm just going to go and kind of walk through a little bit, and this is going to be kind of similar to the curriculum. Might be a little different on terminology, but it's kind of, I think if you understand parts of it, you'll be able to follow along pretty well. So just note that I'm just going to create some random data here, and basically as we kind of saw before with I think generating data, we can generate like a linear regression looking data set. So here basically just pulling out let's see here 30 numbers. So I'm just pulling out 30 random data points. They're normally distributed. with basically our mean is 0. So that means I know they're going to be focused on 0, and then a standard deviation of 3, right? So basically, I know it's going to kind of vary a little bit here and there. And then what I'm going to do, I'm just going to create, because this is right here going to be a NumPy array, I can just use basically broadcasting here to essentially create a little linear regression of what this should look like. Okay, cool. So basically, if you imagine this part, this is what the equation really should be. So it should be a line of slope of 50, y-intercept of 3, but then the data will be basically just randomly generated along that line. Okay, cool. So I have this data point, so just kind of know that exists right now. Now what I want to do eventually is like, okay, I have this data. It's like, all right, let's say I don't know how this is generated, right? So I don't know what this exists or what this looks like. I say, okay, I want to generate a linear regression line to fit the best I can on this data. So one kind of nice thing we can do, we can say, okay, let's make a line. So regression formula, I can basically take in the x, the b, and the a, and that will tell me the predicted y, right? So essentially this will just make it a little bit easier so I don't have to write down b plus a times x. Note that I put a instead of m. I don't know why, I just never liked m for slope. It just makes sense, like why is it m and b? Just, I don't know, there's probably some historical reason, but a and b makes more sense to me, so I put it that way. So just kind of know that's a little difference in case it's different from the curriculum. And of course, I'm not even consistent here, probably because I took this from the curriculum. So next, I'm just defining a few functions like errors, squared errors, and residual sum squares. So basically, it just allows me to calculate that residual sum squares, or RSS. So this is going to be how bad our function is, or our regression line is to the data. Okay, cool. So I got this all together, and now I can actually say, check out our guess, right? So here comes the fun part. So we haven't seen the data yet, and pretend you don't know those numbers. So give me 2 random numbers to make our guess for B and A. It could be anything you want. Not too big though.
Maybe 18, 32.
32. Okay, I'm gonna switch it to, I'm gonna put 32 here, because why not? All right, so we're gonna say our slope is 32, our intercept is 32, our slope is A, and we're gonna plot that against our actual data set, which is this guy right here. Okay, so I'll go run this. And of course I did not import this stuff. There we go. Run your imports. Now we should, all right, so we can see here in the blue dots our data. And we can see here, our regression line is not perfect. It's not bad actually, I would say, like considering, you know, where it's at right now. But you can kind of tell already, not great, right? And so we kind of know this, like just looking at the graph, but if you were just to do this numerically, we can use the residual sum of squares, our error, right? Or kind of our loss, and say, okay, how bad is this? It's like, oh, it's off by this number, essentially. And that's just allowing us to say how much, what's it called? Like just saying how bad it is. So this will quantify how bad our regression line is to data. Okay, so our goal now is to get something a little bit better. So kind of looking at the next part, what would be like maybe your next guess for B and A?
I mean, I would go lower with my, so maybe instead of 32, maybe like 10.
Yeah, 10, right? So you can kind of see your B was 32. We kind of want that intercept down lower. So we'll put something like 10, which looks reasonable, right? Okay, and then our slope, was our slope too big or too small? Was it not steep enough, right?
Yeah, it's not steep enough.
So we probably need it higher then,
Bigger.
right?
Yeah.
Mm-hmm. So
maybe 30.
All right, 30. Yeah, so let's try to run that. And you can see here, okay, not bad. You can kind of see here is that like it probably looks a little bit better. I would argue it looks pretty good, right? You can see it goes through most of it, but it kind of dips down a little bit too low. And we do these numbers here, residual squares, and you can see this number, 4,630, is actually bigger. So I guess we're a little bit worse in this case. You see, and this is where like the numbers might be an important aspect too. And that might be happening that maybe these values over here are closer on like this part versus like they really lag over here. So that could partly be the reason why. I actually find that interesting. Anyway, but we can use this part to basically get better and better. So I'm actually kind of thrown off by that. I hope I did those calculations right. All right, anyway, let's see if we do, so we could just keep doing this. We can keep readjusting, for example, like, okay, maybe B needs to be a little bit lower. So maybe something like 8, right? Or maybe like 5, 5. And then put something a little bit steeper, let's say like 40, right? And we can do that. It's like, oh, that looks a little bit better, right? And hopefully this is a better regression. Sum of squares, I must have that calculation done wrong. Is this X, Y, 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 aha. There we go. Gotta switch those up. So there we go. That should be smaller. And then this should also be there. I knew something looked wrong. Oh, well, duh, because I haven't changed that B yet. So going off of that B, you can see 6,000 and then a better thing over here. Cool. Always right with the world again. Okay, so you can see here, though, we can use, if we had implemented this correctly, right, we would see that this residual sum squares is getting smaller and smaller. And like you can imagine, like, okay, let's adjust that a little bit more. Let's go to like, since we know it's about 50. Okay, you can see here, hey, 282, and you can see it's a lot better. So we can kind of keep doing this over and over again. Or what we can do is like, hey, you know what, we got computers, make the computer do all the work. So what I'm going to do here basically is like, all right, let me just go ahead and have it figure out all the different values. Just try out a bunch of different values going from like, sorry, I'm trying to talk, the different like slope values. So I keep just listening to slope values and seeing basically what is the best value. So this represents our error right here, our RSS. So remember, we're going to call that like our cost function, right? How bad is it? So bigger values are bad. And so we can see here, as we get better and better M values, we get, oh, closer and closer and closer. And it looks like about like 53 is pretty good. And then it starts going up and up and up and up again. Okay. So you can kind of see it's like, oh, we can actually use this to kind of figure out what's the best, what's it called? What's the best slope we have. And note that this is just slope by itself. So in reality, we also have to think about like the y-intercept. So let's just pretend, like, for example, if I change this to 3 now, this might actually get us smaller. So if you see like, I don't know, that's something like maybe 250, maybe like 400-ish, right? Something around there. Or no, I guess, yeah, it's not starting at 0. But if I do this part, you can see it, basically my slope moving a little bit off to the side here, depending on what B value I give it to it. So you would actually want to do this for all values. So like you can imagine this being like a 3-dimensional graph versus just a 2-dimensional graph. Okay, so essentially what we'd want to find is this guy.
Victor, sorry, what was 3 originally? I missed it.
Oh yeah, that was like, I think this was from the curriculum that I had put down from 1.319.
Okay.
So depending,
yeah, that is, okay.
Yeah, you can see if I could do this guy, like for example, you can see my M value is not going to be very good because my B value is so large, right? So we have to find the B value in the M value at the same time, which would be essentially a 3-dimensional graph. But if we just focused on one value, we can still figure out for this y-intercept, what would be the best slope. Okay. So what's kind of cool though is that we have a few things. One is that, hey, we can actually generate this graph. We can generate all the different basically like errors it has. And then we say, hey, we also know with calculus, we can figure out what the minimum value is, which what we want to do here. We want to minimize the error, right? Minimize our cost. So that's where we basically start using gradient descent. Okay. So everyone follow me like on that motivation going from this graph here into gradient descent? Cool. All right. So we just have to adjust it enough and fit for the cost curve. However, there's a slight problem about this. What's one problem you can maybe see about doing this and generating this whole curve and then trying to figure out the minimum point?
I mean, your B is like set.
So one is the B, right? Like we have to also consider B and adjust those too, right? But let's assume like we got the perfect B. Someone told us like, you know, from a pi told us like, oh, this B value is the perfect value, just gotta figure out the slope. Why might not this still be like the most efficient thing to do? It's a little subtle, but one of the problem is that we had to basically just keep going through. You can see here I put 40 to 60. What if I just put like 10 to 60, or let's say I put like 10 to 50. Let's just do 10 to 60. Well, first of all, I have it out of bounds, so that's not gonna work. But what's that? 50 of them, right? No, 40 of them. No, 50. Okay, so you can see here, it's like, I don't know what M value to choose. So I have to essentially just try every single value, right? And hopefully I get to the minimum. If I didn't have this part here, right, then I might have some issue. For example, if I start like, let's say -10 to like 40, I won't reach that minimum value. It's like, okay, let me try again and go further and further, right? And maybe one issue, well, anyway, you can see like there's gonna be an issue with this part, right? So we actually have to kind of cheat a little bit. Say, well, I don't wanna know every value. I just need to find the minimum value. And so this is where our gradient descent is really useful, is that what we'll do instead is we'll step down a hill. And essentially what we'll do, instead of like very carefully walking down every single level, going all the way down, we'll basically take big leaps. And so we'll take a leap forward and leap forward and leap forward. And so the way I kind of imagine this is, you guys all have seen Bird Box, right? Or at least know a Bird Box. Okay. So the whole thing is like, you know, like you're going to cover your eyes and stuff like that. So you imagine essentially when you're standing at this one point and you see the cost function is whatever, right? You essentially are blindfolded. You don't know which way is up and down. But you can probably like imagine like if you're on a hill that blindfolded, you can kind of feel around the mountain a little bit and say, okay, like this direction is steeper and this direction is higher up. And all you have to do is essentially, okay, let me just go down the steeper point. So you can kind of imagine this hill, instead of being like this nice smooth curve, it'll look much more like, I'm gonna draw this in red. It looks much more like you start here and then you take a step, you basically make a big jump downward. And you have this point right here. And then you make another jump downward. And you throw it right here. And so basically you can imagine this line basically a bunch of dots of you trying things out. And eventually you get down to here, like, okay, like, you know, you might overstep it, right? And say, okay, let me go back, right? And so you can basically go back and forth, kind of stepping down this hill. And that's why we call it like gradient descent, right? We're basically using the gradient, which is the derivative, and that derivative is gonna tell us how steep something is at that certain point. And our descent is just basically we're trying to get down to the very small part. Kind of the opposite of this, if you're gonna optimize, is called hill climbing. So you can kind of get the whole idea of like where this part comes in. Okay. All right. Does that make sense? How you would kind of like, you know, if you were a person, how you kind of jump down this hill and stuff like this, and you wouldn't just simply walk down each individual part because you're like, oh, I know it's downhill. It's kind of dangerous, but you can make it work. All right. So kind of expanding it, like I said, like this is just 2 dimensions. We can expand this into 3 dimensions, right? So, and obviously we can actually expand it even further than 3 dimensions, but it's a little hard to draw. So you can imagine this like 3-dimensional hill is that you can imagine this is like the intercept, this is the slope, and this is taken from the curriculum, and this is our cost function. So this is our RSS. And you can imagine this green line representing the path that we end up taking. But if you're like at any single point, like if you're right, let's see if I can draw here. There we go. If we are like right here, what you do essentially is you take the partial derivative. So note that like lowercase d, or not lowercase d, but it's a del. So it's kind of like a d. And you see here is like, well, what you want to do is say, okay, going left or right, should I go left or should I go right? And you basically say which direction is steepest, or like which one is going down, left or right. Okay, and say, oh, it looks like I'm slightly going downhill on the right side. So you kind of move off to the right direction. So that would be kind of like your direction that you move in for intercept. And then you say, okay, which part should I move down in regards to the slope, right? And it's like, oh, okay, well, I want to go up, I want to go down, I'm going to go down this direction. So you say, okay, and you move this part, and then you basically move all together a little bit to the right and a little bit to forward, and that would move you down to this point. And essentially that's how you would kind of feel your way through. So all you have to do, like for partial derivative, instead of just having one part, you just basically feel in every direction that you're looking, every parameter you're optimizing, which in this case is just the intercept and the slope. Okay, make sense? Cool. And the key part is that we know what direction to go based on the derivative. And note that we don't actually have a full picture of what this thing looks like by itself, but we know what the form of the cost is. Like we know what the formula for RSS is. We know what the formula is for this cost function. So we can basically figure out what the derivative equation is going to be and plug that in and say for those values and then figure out what the steepest direction to go is. Okay, cool. All right, so this will lead us to, good, we have plenty of time. So I have a little walkthrough gradient descent part, which I think is kind of useful for us to kind of see like, how does this work, right? So one thing I'll quickly say is that most of the time when you're doing gradient descent, We use packages that are already kind of pre-done for us. We'll see that at the very end. But we can also do this by hand, which I think is what the curriculum kind of shows, like how this looks like. So I have a little walkthrough here. And note that I also borrowed this, kind of adopted, I kind of changed things up, but strongly based on another instructor, Jeff Herman. He has screen descent here. So if you want to check that out too, like what he usually does, but it's more or less the same thing. I just modify something, some stuff and things like that. So let's pretend we're going to have some data. So I'm going to go ahead and grab this data set right here. Note that you can actually find this data set from Kaggle, so house prices. So we're looking at houses quite a lot, right? So we're going to read this in as a data frame and just kind of explore a little bit. We can see like the different values. You can see there's, in this case, 81 different columns. So you can look at these different columns and stuff like this. And, you know, if we were talking about like a full level linear regression, stuff like that, we'd probably use multiple features and stuff like that. But just to kind of show an example for gradient descent, we're going to arbitrarily choose as a feature and target. In this case, we're going to use the GR lives area. So probably the grand living area. There's probably a description on this in the data set. But we're going to grab this area, and then our target will be sales price. Okay. So essentially, I'll grab all of those points. And let's just kind of explore a little bit and see what it looks like, right? So if I plot this out, we can kind of see, okay, here's, for example, on the x-axis should be the living area, and on the y-axis is our target, right, our sales price. And so you can kind of see this is kind of a nice feature to kind of look at, right? At least to kind of get the idea. Like you can imagine where that line probably would fit, right? So kind of quickly looking at this, what are some quick issues that we might have when we're building our linear regression line?
The outliers above 4,000.
Yeah. So how about, I was gonna say, you know, like what are the outliers that you guys would say? If you guys want to like draw on it, like, I don't know if you guys have done that before, taking my screen and kind of annotate, you can just circle which ones are the outliers. And I think all of you guys can do that once too.
Just those like bottom two. Right?
So just these two?
Yeah.
Okay, yeah, probably, I see some nods. All right, so let me ask you guys, are there any other outliers that you should worry about here?
I mean, maybe those two above, but I feel like the line kind of looks like it would be going through them.
Good, yeah.
Why not keep them?
Yeah, no, I think that's actually the right thing here. In this case, for just 2 dimensions, is that even though they're kind of far away from the majority of it, if you imagine where the line is without these, the line would probably be something along like this, right? And so it probably goes right through those parts. These definitely should be removed because they're so far off to the side. They're so different from the rest of them. And remember, that's an important aspect of outliers. It's really different from the rest of the group. And that's why we're removing it. If we kept those in there, our linear regression line, right, well, the way it'll form, right, it'll kind of go off to the side, right? It'll kind of get pulled down by these outliers. So we don't want that. If you remove these guys, and let's say we remove these ones, if you remove these guys, the linear regression line probably would be about the same. Like it probably wouldn't be affected that much. So we're probably fine keeping it in there. Cool. So just kind of removing those outliers, then we can kind of see we're just removing everything to the right of this 400, right? So like you can remove these ones. We don't remove them. It doesn't really matter too much. I'll just keep them in there. Or I guess I'll go ahead and write this. And this is from before and then 300,000. So this just makes it a little bit cleaner for us to check it out. Note that you didn't necessarily have to remove all those aspects, right? But just kind of like clearing up a little bit. Okay, cool. All right. All right, so let's go ahead and go into our actual linear regression line, right? So just like before, we're going to define our regression formula with our x, our slope, and our intercept, right? So our classic, you know, line equation. So we have this guy. And then what we're going to do, we're going to start off with essentially like, all right, let's just like set everything to 0. And usually classically, we'll set things to 0 or you randomize it. But 0 will kind of show how like bad essentially this first guess is and how we can actually improve every time. So in reality, though, you probably, just for the record, you probably would use randomly. That way you don't start off at 0 and kind of guess. You're more likely to randomly come across it than always starting at 0. Okay, so if we look at this now, our regression line and our thing, and it's kind of hard to tell, but that black line right there is our linear regression line. So you see, pretty awful, right? So like it doesn't predict anything at all. And again, if you guys remember, the basics one would be like the average. So probably like the average would probably be like right about here-ish, where you would have like a straight line going through. Okay, so to kind of define what this error looks like, essentially what we'll do, we'll basically say, all right, take our yi, which is going to be our actual data point, right? So what's the actual sale price? And we'll calculate from the linear regression line, right? Basically say, okay, what is that value supposed to be? What is our predicted y? So taking that specific xi point, so any given point, plus the intercept and slope, which doesn't change for our regression line. And then we basically take the difference between these, square this, and this will give us basically our total error for this part. And we can use this now essentially as our cost function. And you can see here, I mean, doesn't necessarily mean anything by itself, but you can see it's pretty decently large, right? We want this as closest to 0 as possible. Okay.
So Victor, quick question.
Yeah.
So you're using error instead of like the residual sum of squares for the cost function here. Is that different? I don't know. That was different than what we did, like just did.
Yeah. So the residual sum squares is very close to this, right? If you look at this, essentially what we're doing is the difference between each one, right? And then we're squaring it. So we're still doing that squared part. The one part we're not doing is like the the square root of it. And the reason why is because essentially if you imagine a square root is that even if the value is, what's it called? If the value is like, if one, let's say value A and value B, value A is larger, if you take the square root, it'll still be that B will still be smaller than A. So it doesn't really affect us since all we really care about is like, oh, we just want to get the error smaller. So we're just kind of skipping over that part. But if you look at this, this is really close to what we pretty much do. It's just kind of a little slightly simplified form. Okay. Cool. And note that we still divide it by n. Oh, sorry. Yeah, cool. All right, so we got the error. So essentially we can say how good is our function, right? So let's move on then, say, all right, let's take the gradient. So this is the part that's a little subtle, that I think sometimes gets a little confusing. So I'm gonna kind of walk this part through. So in order to proceed to gradient descent, we actually need to find the derivative. And remember, the derivative is not of the linear function, right? It's not the function that we're trying to use to predict. It's actually the loss, right? So basically how bad of a fit is our prediction. And so since our error here is basically how bad is our fit, that essentially is just saying, hey, we just need to take the derivative of this guy right here and saying when we put in our model. So you can imagine putting our model in right here. So what we'll also do is also take the derivative with respect to B and respect to M. That way we can adjust M and B at the same time. Okay. If we care about just one, we just basically, I should say A here. But we're basically going to adjust the derivative, adjust the slope A and the intercept B, right, until we get this right. So we can pre-calculate what the derivative should look like. Essentially, what does this function kind of end up looking like? And if we do this with respect to B, we end up getting 2 times, y, which is going to be a single data point, minus A times xi plus B. And it's kind of similar thing if we do something with respect to A, we'll get this extra factor of A out here, or this extra factor of A is being multiplied by xi. So we'll actually get times xi in the front here. So just kind of know is that all we're doing here is just taking the derivative of the loss function. So sometimes you'll see this as, I'm just going to put a little letter here. Sometimes you'll see this as, well, it's usually a fancy L, but oops. It'll look something like this, ignoring all the stuff to the right, like the derivative of the loss with respect to B, or derivative of like the cost function with respect to B. Okay. So just know that I could have put any function off to the right here, whatever we're using to measure how bad our model is. Okay. Does that make sense to everyone? Cool. And I won't go through the derivative process, but you can see basically it's the chain rule going on here. Okay. Cool. So I'm just putting this in here to make it a little bit easier for us to kind of like see it when we do the code. But basically, I'm just doing the partial derivative. I'm just reiterating that derivative right here. Actually, I realized too, this should actually be 2. Not that it really matters, because it really shouldn't matter because we're just talking about like how big a value is, but I'll keep it in there because that's the actual derivative. Usually these constants kind of get fallen out because just for simplicity. Okay, so I have my partial derivative here. And then what we'll do here, oh, that's why I got rid of it, sorry. Yeah, I'll keep it like this. There we go. Sorry, I realized why I put 2 there. So this is the actual derivative. And then what we're going to do here in the step gradient, every part we're basically saying B and A, X and Y are basically the whole data set, right? And we're going to have our gradients, our dB, our DA. So that's kind of like how much we should adjust our A or how much we should adjust our B on that step. We're basically kind of like feeling the mountain and saying how far should we go. Note that we have this learning rate, which I haven't talked about yet. Have you guys looked at what learning rate is? Okay, so who would like to explain a little bit, like what is learning rate? What's it doing?
The point of it is to help you not overshoot the minimum. And it's like a little fraction that you're going to multiply by the update that you're making every time, just to make sure that it doesn't get too big.
That's right, good. And the way I kind of imagine this too is like on our hill analogy, if you're blindfolded, instead of taking like a huge giant jump forward and like possibly like overshooting, like, you know, if you imagine like you have this curve and you're overshooting that, like you said, the minimum, it's kind of like, well, we'll take it like a modest jump. And essentially the learning rate is saying, how big of a jump do you go forward? If you take 2 small jumps, you take like a step each time, it'll take you forever to get down the mountain. But if you take 2 large of a jump, like you take a huge, massive one, it's likely that you'll end up skipping over the minimum. And then you'll find, oh, I'm too far back. And you go back another hill and go back and back and back, and you'll never get anywhere. So that's why we do this learning right here. Okay, so cool. All right, so then what we're going to do, we're going to find our gradients, and these gradients are all going to be affected by each individual point on the data set. So essentially what we're going to do here, we're going to update our dB and our dA by taking the partial derivative for that specific data point, okay? And then we're going to go in the negative direction. So remember, we're going to go in the opposite direction of the slope, right? So we want to go down the hill. So that's where that minus part is here. Note that I did the divide by n here. That's because at the very end, you could technically put divide by n right here. But I'm just putting it in here just to kind of make it consistent going through, but it doesn't have to go in this part. So basically, we're taking the average essentially of the, like how each data point is telling dB to move towards, okay? And note that dA here, same thing. Cool. All right, any questions? Looking pretty good right here, at least this part. Okay, and note that usually you would find the derivative ahead of time. If you were to have some other funky function, you would figure out the derivative ahead of time. You wouldn't normally just have it just put in here. Okay, and then what we have is like, we have our derivatives. We just essentially move downwards by a certain value, and this should be plus. Come on, Victor. Okay, so essentially we're just going to add that onto our value right here. And remember, we're just moving in that negative direction. Okay, cool. So run this guy right here, and so we'll get our first iteration. So we have our first step right here, our step gradient. We're going to basically take from our 0, 0, right, from originally, and we're going to adjust it. And note that learning rate of 0.1. So we're just kind of doing this one step at a time. And you can see here, our new values are these negative points. Okay, I actually wonder now if this should be, well, we'll see. Yes, I was wrong. Pass, Victor, you were right. Forgive me. There we go. Yeah, it's a little bit better, right? So you can see here, it's pretty significantly far off, right? So you can kind of imagine like, okay, this isn't quite what we want here. So what we're gonna do next is like, okay, let's go into the next part. And you can see our error is pretty high. So one thing is that we have our learning rate, which is way too high. If you look at 0.01, right? Which is probably too high. It took a huge leap forward and didn't know what to do. So what we'll do here instead, we'll take a moderate step forward. And you can see, okay, good. Like it inched up. It just kind of went up a little bit, but that's what we want. We don't want it to overshoot like we saw way over here, right? So that's kind of like what we're going here. And you can see the error printed out is the error is a little bit smaller compared to, what was the first one, the first step? Some ridiculous number, right? So you can see, not great. But this is a lot better than our first initial. You can see it's by a factor of, what's that? I don't know, some trillion number or something like that. Okay, but we're moving in the right direction. Slowly, but we're moving. Okay, so next thing is going to do our second iteration. So we use the same learning rate, right? And basically we'll use our first step, right, that we kind of stored over from earlier. And we'll take that first step right there. We'll take what's it called? The y-intercept and then the slope, and then we'll modify it from there. So we run this guy. And so hopefully we'll get a little bit better than this, right? And you can see it's moving up, right? So you can kind of see it going up a little bit. You guys see that difference right here? And so note that, like, you know, depending on what is going on here, like, oh, you might want to adjust the learning rate or whatever. But we're also going to do this over and over and over again. But I'm just kind of going step by step by step. Okay, cool. So our third iteration, same thing. We take our next part right here, and then we'll do our learning rate, and then we'll run it again. And, oh, I didn't run this guy. There we go. And then you can see me move slightly better, right? So you can see it's getting better and better, and you can see the error is getting slightly smaller now, right? And so the idea here, we just keep iterating over and over and over again until hopefully we iterate enough time for like that's enough iterations, or we say that's good enough, okay? Cool. Do you guys have any questions going from this first iteration, second iteration, third iteration? Okay. And you can see now the importance of the learning rate of saying like why you don't want a huge learning rate. You want something that's going to modify. Typically your learning rate, just for the record, is usually something around like a value around like this value, give or take, depending what you're doing. But this way you can kind of see it slowly go up without us overshooting. Okay, so let's try to do multiple iterations. Okay, so this way we can automate this stuff. You're like, okay, I don't want to do this all day, going through each iteration and running over it. So we're gonna do a for loop, right? So we'll say, okay, we're gonna do 100 iterations. We'll start off with 0 and 0 like we had before. And basically we'll keep the errors just for us to kind of check out and see what that looks like. And we're basically going to keep going through and updating B and M each time, okay? So if I run this guy right now, you can see it kind of takes a while. And I'll run this once it goes through. And note right here, I have an extension that will time how much it takes. So once it's done, it will say how long it took this whole thing. But you can see here, it took about 10 seconds, right? So it took quite a while for it to calculate 100 iterations going all the way through, right? And you can imagine that's because it's going 100, each step is going through the whole data set as well, right? Checking out each part. And you can see here our range of errors. Remember, a low error is good. And you can see here, we did fine. Like we got a pretty low error. It looks like pretty close to 0. However, you notice I didn't really get much better after like 40, 60, right? Like it definitely like leveled out right there. And you're like, look, like it technically did better, maybe, but like, is it really that much better? It's close enough. Like, and you can see that took us 10 seconds. If this took us like 10 hours, let's just make us a number, 10 hours, you'd be basically wasting 5 of your hours at least. So just kind of waiting for this thing to finish when it pretty much figured out the smallest thing. So we can do something called early stopping. So early stopping allows us essentially to take the value and say, all right, if you, one thing we can do to early stop is say, hey, go 100 times, but if the error doesn't change by that much, then let's go ahead and just like stop it there, okay? So you can see here, that's what we're doing here, essentially saying, oh, if our error doesn't change by 1%, we'll just stop it there. Like you don't need to keep going, right? And we can see where it stops in this case. So we'll print that I here. But basically the code is exactly the same except for this part, okay? So if we run this now, and remember this took about 10.6 seconds. If we run this now, we'll see how long this takes. 4.92. So you can see it basically cut in half, which makes sense about halfway through here. And we can see we stopped at the 47th iteration. So right here. And you can see this error. You can see it basically finished at this part right here, and it got a good enough answer, essentially. If we wanted to have smaller than 1% difference, we might have something different, or there could be other parts where say when the error hits this certain amount, we could do that as well. But basically the idea is that we don't want it to change. Like once it's not changing much, we can pretty much stop, okay? Cool. Everyone understand that so far? Awesome. And what we can do here, so this is kind of fun. Again, this is borrowed from Jeff and stuff like that, kind of adopted. So he kind of put this part together where essentially you'll do this 100 iterations. So we saw this kind of like working in the background, like not knowing what's going on. He made it so that basically every 10 iterations, you can see what the linear regression line looks like. Because remember, these errors are represented by that linear regression line. So what this will do, basically, we'll go through these iterations and we'll plot out the error function, so the whole error, and then each linear regression line. So you can see here after 10 iterations, the line's about here. After 20 iterations, right here. After 30 is right here, 40, and it keeps going through. And you can see basically after 50, the line really doesn't change that much, which is represented by that error kind of like not really changing. And one thing you can basically end up having is your line can basically fluctuate back and forth, back and forth, back and forth, back and forth, and not really like do anything. So it's kind of hopping back and forth towards that thing. So like you're like, oh, the error is really not changing by much. So you can see at the 90th iteration, it pretty much looks the same as probably like after 50. So you can see here, like it's a little bit different. You can tell there's kind of goes through these lines, but it's really not significantly different. So you can probably just stop there. Okay, cool. All right, so you can see how that whole process would write out, like making that gradient descent. So what we can do instead, if we don't want to write all that stuff, we can use the shortcut method, which honestly, I'm not saying like you should always just find the quickest way. We should find the most quickest way that's useful, but also a lot of these packages are tending to be optimized. So one thing you might notice is that we did a lot of for loops. For for loops are not usually the best thing for us to do because we can't vectorize it. So this time we can't really do much about, but even finding like the, let's see here, where did I find this? When we found the gradient descent, or when we, when we did the stepwise, this would not be the most optimized form. You probably want to vectorize this so that way you can just basically push all the data points through it and then go from there. So note that like this isn't super optimized. So what's nice is that they're really, really smart people who work in collaboration with each other with open source and say, hey, let's make this really optimized. So these packages usually tend to do very, very well. So we import a linear regression model, linear regression, right? Just saying, all right, we're doing linear regression fit. And we basically say here, does dot fit? And you can see these X values. Basically, it's doing some reshape and so to make sure that it takes in the right values, essentially like as what it is expecting. And then this dot fit right here, basically it's just doing linear regression for us. Note, or not linear regression, gradient descent for us. And you can see here, we can actually see some values here. For example, there's kind of some more documentation of what you can do. But once you have this, you can go ahead and run this through. And you're like, cool. Like basically it fit it, it's done, right? So you can kind of see what the coefficients are. So these, what's nice about sklearn actually has like these different variables right here that will actually tell you what those values are supposed to be. So you can see here our coefficient for, what was this one? I think this is B, and this is B. And I think this is, oh, maybe this is B. I actually don't know now. I'm trying to think real quick. Oh, this should be 1. I believe so. No. Sorry, I'm kind of thinking in my head a little bit of which one's the y-intercept. Oh no, okay, I'm sorry. Coefficient, this is the slope, and this should be the y-intercept here. Okay, so if we kind of plot this out, what this looks like, you can see here, here's the one from sklearn, and here's the one from gradient descent. Note for us, which this shouldn't be B. I don't know why this is showing up here. Oh. I actually don't know why. I'm not sure what Jeff put on that one, but I think he was trying to compare the two different values that we had from like B and whatever was from right here. I don't think this was stored. No, it was stored. That seems wrong to me. Sorry. I'm kind of like talking to myself. So supposedly the gradient descent from here is 0.7 or 0.07, but that seems unlikely. I think that something's different here. But you can see here basically the sklearn and the gradient descent are more or less the same thing. And that's because they're using the same strategy to find the, what's it called? The line of best fit. Okay. And you can kind of see some error here. So you can see like the mean squared error. So if you take the square root of this, for example, you can see we can get this whole value right here. I like to say like I don't really like using the error as like oh, how well did it perform, because it's much more using a metric to say like how well it fits each time. So each iteration is using this error. So that's why I don't like talking about like the error by itself as a metric, because it's a little vague. But if you get something like r squared, you can use the error like the RSS, right, to get the r squared to get an idea of like how to compare these with traditional like lines and lines of best fit. Okay, so cool. Yeah. So do you guys have any questions then from anything kind of followed through? No, pretty good. Yeah. So yeah, just kind of know is that gradient descent, essentially that's what when we use back in like linear regression.fit, if you guys did this in your mod 1 project, that's essentially what it was doing in the background. You probably didn't even know. So cool. All right. So I guess I'll go ahead and stop it here.